Hello, everyone. Welcome to this afternoon general session for SciPy 2021. Again, I'd like to thank you all for attending. The general track is for talks that aren't domain specific and are generally applicable to all different aspects of scientific Python. For those of you that want to ask questions, we have two options. There's a Q&A where you can type a question, or you can raise your hand and we will bring you on stage. We're aiming to have 5 minutes of questions at the very end. So if you would like, please do raise your hand. Then you can turn on your video and ask a question as you would at an in-person meeting. But without further ado, I'd like to introduce our speaker this afternoon, Nicholas McKibben, to talk about a review of linear programming for Python.
All right, great. Thank you. We got lots to get through, so let's go ahead and go to the next slide. All right, so what is a linear program? A linear program is simply an optimization problem with a linear cost function and linear constraints. You can read programming here as optimization. LPs have found applications in optimization theory, engineering, business, telecommunications, lots of places. Presumably you showed up here because you were interested, so I'm not going to try too hard to convince you of their utility and importance. You can read up on Wikipedia has a lot of good stuff on it. More interesting problems exist that don't fit the description of LPs, but LPs turn out to be useful in solving those more interesting problems. LPs are generally written in a standard form, and that standard differs based on who you asked very usefully. We'll use Wikipedia's version because it's fairly ubiquitous and might be the way you write a problem on paper before trying to code it up. On the right, we also have, you can see the vector matrix representation of the same problem. The cost coefficient vector C variables we're trying to optimize are over X in the constraint matrix A with right-hand side B. There's also generally a non-negative constraint on X, but we'll go ahead and allow arbitrary lower and upper bounds on X because it's really easy to do, and all of our solvers will support that. We don't really want to explain or focus on optimization theory. Instead, we're looking at the Python software ecosystem to quickly and easily solve these types of problems. What we have in mind is a resourceful person, not necessarily an expert that needs a problem solved. They wrote down the problem maybe on a whiteboard or a piece of paper and now wants to use a computer to solve it. The next slide. Let's quickly talk about how we arrived at the packages we did. The ones are in that column called package. Those are the ones we're going to look at. The tools in Python these are the ones we can use to solve linear programs. I myself am a busy engineer who has lots of things to do today. The tool I choose has to just work. So we're considering packages that work out of the box across all the major operating systems. They need to be able to be installed without much pain through the official pip packaging system. Conda is really nice, but if you don't have it, you don't have it. And we also only consider the LP solvers that come prepackaged. Again, our hypothetical user is busy and doesn't want to muck around with installing build tools and getting solvers built. There's also a consideration here for permissive or copyleft or academic licenses. We didn't consider any commercial solvers in this presentation, even though some of them are very good with well-maintained Python interfaces. We'll leave that as an exercise for the reader. On the right is the evaluation of these criteria for the packages we'll consider, including licenses, package solvers, all the things. I don't know if these slides will be available afterwards, but if you get in contact with me, I'm happy to share it. The one thing to notice is that there are two different things happening in the Python linear programming ecosystem. There's problem modeling and problem solving. Sometimes these two activities are integrated into the same package, but because we're trying to focus on the solvers as a scoping mechanism, we're going to consider packages that are well-known and well-used, like PULP, Pulp, and Pyomo, more modeling focused than solver focused. They also sometimes rely on inefficient invocations of solvers, which we'll discuss later. And for a variety of reasons, we've not included them here. Another casualty is LPsolve, which I personally found very difficult to install in Linux, but I hear it's fine on Windows. Scikit GLPK is a small package that I wrote using C-types bindings, and I include it here mainly to compare against other GLPK solvers in wrappers. We're also evaluating SciPy's highs solvers, not the Python simplex and interior point implementations. Another note and something to be aware of is that more advanced solvers will be able to handle the simpler kinds of problems we're talking about, like linear programs. However, they may not be optimized for these simpler problems. Mixed integer programming, quadratic, nonlinear cone solvers might apply checks and redundancies on the problem and be less efficient than specialized, simpler solvers. For this reason, we choose to focus on a narrow set of LP solvers that are available in Python shown in that table. So next slide. Quick comparison to do. We'll get through this pretty quickly. This is a truncated list of features available from the solvers in each package. Most provide both primal and dual simplex solvers, and all include interior point methods. SciPy is the only package to lack MPS and LP file format read-write functionality. There is functionality provided by Highs, the SciPy's integrated solver, but it is not exposed as a public API. There's also problem sensitivity information reported by all solvers in the form of duals or shadow prices. And this is also newer functionality for SciPy. All of these packages support sparse constraint matrices, which is very important when you consider large problems. And curiously, none support callbacks that I could find a well-documented way to do it. SciPy's Python solvers do have callback support, but since we're not evaluating them, we say no here. All packages except for SciPy, scikit, GLPK, and CVX opt are able to construct linear programs through arrays and matrices directly. Not except, sorry, they are able to do that, but the rest require a modeling language to do the setup and validate the problem. Let's go to the next slide. All right, so now we have our tools. We want to know what they're like to use. Remember, we're busy engineers and scientists, and we need to get stuff done. Different solvers can behave in very different ways, so right now we're going to throw a short battery of problems at them and see what we can learn. We have class examples that you might remember from a beginning optimization theory class, and we'll throw some trickier, harder, and larger problems at them, as well as talk about some direct applications where LP solvers are incredibly valuable. We can also show some specialized algorithm performance on assignment problems that can be formulated as LPs. That's just a little bit of fun. Some notes here about the machines we ran the problems on and validated the package with. Very big thanks to the University of Utah College of Engineering for letting me SSH in and do these tests. So let's go to the next slide. Dive in. All right, next slide. To get warmed up, let's look at the classic and well-abused example for LPs, the diet problem. The problem is, given a set of foods, nutrient information, dietary needs give the optimal dietary recommendation. In the top left, the LP formulation you would write is right there. There's not much interesting other than to say it's a pretty small problem. Our data set was 22 constraints and 64 variables. The exercise was to go from this LP definition that we wrote to a solved problem. And the graph, or that bar plot, shows the time to optimal solution for each solver listed along the bottom. The cost function value at the optimum is on the top of the bars, and they all agree, which is very heartening. The SciPy solvers are the far bottom, far left. You can squint to see it. Sorry about that. And they're the Highs dual simplex solver and interior point. There's also the scikit GLPK, both the dual simplex, primal simplex, and interior point. And then you got the OR tools, GLOP, Google's linear programming solver. There's the SciP and CLP wrappers, and then followed by CVX opt and CVX pi. The CVX opt is using a cone solver and another GLPK simplex wrapper to compare against. The CVX pi, ECOS, OSQP, and SCS solvers are higher level solvers, and they're on the right there where you see the big bars. And they're not necessarily optimized for LPs, which we can see from the relative performance. So that's just the very basic one. Let's go to the next slide to talk about how we went from that problem formulation to the actual problem. So like we mentioned, there's two package approaches. There's the matrix style and the modeling language style. On the left is the matrix style. It's very straightforward. Given a spreadsheet, I use NumPy to parse the comma-separated value file and load values into arrays. And then there's a quick code snippet there where it's unpacked into the appropriate arrays. We do have to convert a greater than or equal to constraint to a less than to match the standard form, but that's pretty easy to do with a couple well-placed negative signs. SciPy and scikit GLPK allow you to specify LP models like this straight from the matrices. CVX opt allows this as well, but its standard form is different than Wikipedia's, and I found it to be much quicker and easier to use its modeling module. Speaking of, CVX opt and CVX pi and OR tools all use modeling languages. To demonstrate what this looks like, an OR tools code snippet is shown on the bottom right there. Following Google's documentation, the intended way to construct the model is by looping over all the cost coefficients, bounds, and constraints to unpack the solution. It also requires looping over the object. Reading around, it appears that the OR tools maintainers would accept a PR for NumPy integration and matrix interface, but they aren't working on anything and don't seem very interested in that. I found that CVX-opt and CVX-Pi were better with support for NumPy, but the thing to take away here is that there is some overhead in model construction that will come up later. Let's go to the next slide. To investigate the scaling performance of the best solvers from the previous diet problem, which were the SciPy and OR tools, let's look at another example. This time it's really, really simple. It's just I've generated random cost coefficients, bounds, and constraints at various sizes, and we're scaling them up and looking at them. The top left image shows the time from the solver's start to optimal solution for SciPys and OR tools packages, including the time it takes to construct and validate the models for OR tools. Excluding, sorry, this is just the solver, not the model part. The number of variables n is 2.5 times the number of constraints in this plot, so we're testing out the solver's ability to handle large numbers of variables compared to constraints, or I call it here column scaling. To the right, if you go directly upper right, we see a row scaling version where the number of constraints is 2.5 times the number of variables. Again, this plot only shows the solver time, no modeling overhead. From the two top plots, we can see that row versus column scaling, while there are slight differences, it's actually pretty close. This means if you have problems that looks like this one, you'll be fine using either. Now let's examine the lower right plot to get a more complete picture of what's going on. This is solver time plus the model time, so including the time it takes to construct and validate the model. While OR tools, GLOP and GLPK were winning in the upper two plots, now SciPy's highs solvers are doing much better. That's because it takes much longer to construct the model, and it gets worse the larger the model is. I was actually confused for a long time about what these plots were telling me, because my lived experience of time was telling me otherwise. So I started to look into it, and that's why there's the modeling overhead. Let's go to the next slide. Another application of linear programming is robust regression, or L1 regression. I've again created some random training data. It's described in the top left. A normally distributed stochastic feature map to map that data to a space, and then constructed the sparse constraint matrix and cost vector appropriately to do the regression. This turns out to be a little bit trickier of a problem and a much larger problem. Scikit, GLPK, and some higher order solvers can't handle this problem and start spewing warning and error messages. Interestingly, CVX-ops GLPK is tuned differently than Scikit GLPK and can find a solution to the problem, while Scikit GLPK can't. Some solvers report an answer, but in fact give the wrong answer. I was surprised to see CLP, which is a very well-known and respected solver, do so poorly on this problem. I think that if you delved into the modeling languages for CVX-Pi and OR tools, they have specialized functions and objects for L1 objective functions, but the actual LP definition fails to run with the default settings. Remember, we want it to just work and as little pain as possible going from our problem on written paper to code. So let's go to the next slide. All right, this is more stressing the thing, and this is actually more of an interest slide than an important slide. So if you define an LP with multiple optimal solutions, which might happen, what will the solver do? The LP description is on the top left. It's very simple, only two variables, and the graphical description is on the right. The constraints cut out a plane into a feasible white area, and all the points along the line pointed to by that black arrow are all optimal. Anything along that line will work. Most LP solvers get the same answer, interestingly, but some don't, and the higher order solvers can be all over the place on where they decide to end up on that line. I found this to be an interesting way that solvers might disagree with each other, even if they all get a correct answer. And also note that the modeling languages didn't catch this case where there were multiple solutions. So it won't catch it for you. You have to design your LP to either do this on purpose or make sure that this doesn't happen. Next slide. All right, so a famous problem in linear programming is the Minty cube. It's a pathological problem designed to show the worst case performance of simplex solver and others like crisscross algorithm. This will also do that for that. These were interesting performance profiles, so I wanted to take a quick look at them. I split the solvers into three groups based on performance to make the plots less cluttered. The first one, the furthest left, are the GLPK solvers, and they show a split between the C-types wrapper in Scikit GLPK and the raw C Python interface provided by CVX-opt, which is, I've looked at the code, it's very well done. So there will be some performance differences depending on what type of wrapper you use. Directly to the right is SciPy's highs, and the OR tool solvers are also interesting. Lots of noise even at the 50 averages for the beginning of the SciPy solvers. But it overtakes GLOP about the time where the integers get too big for the computer to handle, up in the top right. The higher order CBX opt had lots of trouble here, as well as GLPK's interior point and CLP. You can see where the lines stop. That's where the solvers conked out and said, I can't do anymore. So some observations, simplex solvers appear to be more robust than interior point algorithms. This is something that lots of people have observed before, but this is just confirming that for our Python interfaces. Higher order algorithms take much longer to run and fail much more often on these pathological simple LP problems. So that's interesting. I will also note that unlike previous plots, this is measuring solver time only, not model construction. So talking about start of to finish time of modeling and solving, highs is going to beat the OR tools in that top right plan. But if the model is already built and available, this would be the performance you would see. Next slide. All right, the netlib benchmark suite is well known in the optimization community. I've taken a smattering of them and omitted some of the cases I know take a very long time to run because I didn't want to sit here twiddling my thumbs. Solvers start at the bottom of the far left. The left-hand side is the list of problems. So the solvers are going to work their way up, and time moves to the right. So while they travel upwards through the problems, they also drift right as they take time to solve them. This is taking into account modeling and solving time. So while the curves are similar, the modeling packages consistently take longer, as we've seen before. And I've also omitted some of the packages here because I know that the higher level solvers are just going to take forever to chew through these things because of the modeling and some of the performance characteristics. So this is interesting to see over a wide variety of very useful and well-known problems, which are the netlib problems. Next slide. All right, this is a cute demonstration of how a lot of graph algorithms can be formulated as linear programs. In this case, it's an assignment problem with cost for assigning something from a set A to a set T. The constraint matrix is such that only one thing can be assigned to one thing, and that's where the lower right-hand corner, you see a whole bunch of ones, and that corresponds to inner products, making sure that everything is equal to 1. Because of the structure of A, we actually have satisfied a property called the total unimodularity property, and we get an integer valued solution for free. You can read about that. It's pretty neat. We're obviously slower than optimized and specialized algorithms for this problem, which is the Hungarian algorithm, the solver from the SciPy's optimized module. But for your trouble for doing this as a linear program, you get sensitivity analysis information, you get the duals, and a way to fiddle around with the parameters of the problem that you might not have had. You can treat the Hungarian algorithm as kind of this black box where you pass in your information and then it does something to it. Whereas with a linear program, you can look and see, oh, what happens if I change the matrix like this? Can I change the problems? That's an interesting way to interact with these graph problems. Next slide. All right, so I'm sure many of you are aware that LPs are old news. They're very simple. All the real world problems we as engineers and scientists look at and try to solve are often much more complicated and have much more complicated constraints and integer and binary constraints on the variables. I wholeheartedly agree. LPs are the basis of most mixed integer linear program solvers. At my day job as an autonomy engineer, I implement and prototype really complicated algorithms, much more complicated than linear programs, using LP solvers like the ones shown in this presentation. When I read a paper, they describe specialized heuristics or a novel algorithm not implemented by any MIP library that you might be using. So you have to write your own sometimes. And when you prototype, it's fantastic to have these tools in Python for doing it. Lots of papers will also use LPs to bound NP hard problems if you're a computer science guy. Business people use them in complicated decision processes. I've mentioned the LinMap. It's pretty old, but it seems to be still kicking around for multiple attribute decision processes. Both matrix style modeling interfaces and modeling language interfaces work great here when you're doing these prototypes, because you have to make the model once if you consider like a branch and bound, and then you can make small cheap alterations going forward. So those bottom two plots, are showing the objective function plotted against iteration number of a pure Python implementation of a branch and bound that has some different heuristics I was adding, and just comparing different LP backends. So that's one of the strengths of being able to have these linear programming tools in Python available. Next slide. All right, so what did we learn? Can we summarize some of the key thoughts from what we talked about? So this is kind of a tale of two kinds of packages. There's the matrix style and the problem modeling style. And not all solvers are available in both kinds of packages.
Nicholas, you have about 5 minutes.
All right, great. We are getting finished up. You might want to choose a package based on what kind of problem modeling you're going to be doing. There's also been increasing interest in getting Hi's, Pyomo, and Pulp integration. The Hi's team welcomes any Python expertise. I know they don't have a lot of people on their team that are familiar with it. So if you're looking for somewhere to contribute, maybe go pop your head in there and say hi. Dual simplex and interior point algorithms kind of dominate this space. That's what you're going to be running, really. And they work really well over a wide variety of problems. Simplex we found to be more robust. Interior point can be faster on some problems, so try it out. Calling solvers via the command line and files is going to lead to a lot of file I/O overhead, and that's kind of what Pyomo and Pulp do. They have backends where they pull from files and call things on a command line. Model setup costs can be significant. Again, adjusting tolerances is a useful way to improve solutions. We like I said, I'm a busy engineer. I tried things out of the box, but if you're sitting down trying to solve a problem working with these packages, what you want to go in is try to find those knobs and turn them. Slide. All right, so the kind of gaps that we identified here were that primal simplex is in general less available than dual. That's better for if you're doing mixed linear program. There's also some exotic algorithms that never really caught hold the way that simplex and interior point did. Cassowary is used for GUI layouts. Sometimes there's also ellipsoid methods that are more like constraint generation algorithms. There's other ones. It's not clear if these are useful, but we don't really know because we don't use them a lot. So it'd be interesting to see more support for those weird algorithms somewhere. There's also limited information available, and that's during runtime, and that's related to that there's not a lot of clear callback mechanisms. So after each iteration, you might be wanting to run a callback function to get some information. And that's needed for solving super large problems. Use something called constraint column generation, or I've heard people call them lazy constraints. And there would be more runtime monitoring ability to interact. We're also lacking support for some lower overhead LP model construction. In some cases, OR tools has no clear, efficient NumPy interface to it. Next slide. And to finish this out, so the Python LP ecosystem has out-of-the-box support for most popular permissively licensed softwares. It's great. SciPy now distributes advanced Hi solvers just out of the box. It will work on your system if you have a wheel for it. More advanced solvers are equally available. So if you talk about MIP or cone solvers, quadratic programming solvers are available in all of these packages. Advanced model creation analysis supported by lots of places, very popular. Lower level interfaces have sizable benefits when solving small medium-sized problems. We saw that comparing the CPython interface for GLPK to the C-types one. There are also many opportunities to contribute. Hi's modeling package integration. We're thinking about in the near future getting a MIP solver from Hi's into SciPy. And then there's also just general MIP solver integration testing for other packages. There's also room for improvement would be callback support. I would love to see some more support for that. It exists on the low level for some of these, but they're not available in the public API. I'd also like to see some help for expensive model construction overhead, maybe avoiding that if possible, and then getting filling in some gaps with file format read and write support. And that's about it for this this presentation. We had a lot of fun doing it. I don't know if there are any questions or anything. I know Matt's been lurking in the comments. We can try to.
We've got one question in the Q&A.
Well, we can give, first of all, the speaker a round of applause, I think, for a really great talk. And then, yes, we have a question in the Q&A. This is from Tetsuo. You can correct me if I said that wrong. Is SciPy and OrTools wrapping different library? What is the purpose of difference of speed?
Yeah, so they all are wrapping different libraries. OrTools is a more of a modeling package that has backends for Google's own. They've released an open source solver, GLOP, which I've heard it's used for some optimizations and YouTube algorithm recommendations. Very, very powerful, very useful, and you get a high level interface to that through their OR tools. It also wraps, I think it comes prepackaged now with GLPK, which is another open source one. There are also optional solvers that you can install yourself, and then OR tools will be aware of that integration. Whereas SciPy has the high performance linear programming library written in C++, is now packaged with SciPy, and it was actually Matt Haberlin and I wrote an interface for that. So we're the ones that integrated that into SciPy, and it seemed to be working really well. Haven't gotten a lot of complaints there. Lots of speed performance improvement.
Great, thank you. Thanks for answering that. Does anybody else have any other questions? You can feel free to ask in the Q&A, or if you'd like, you can raise your hand and we'll bring you on stage. Okay, we got another question. I'm going to show it on stage from Evgeny. Please correct me, I'm so sorry. Have you tried comparing the performance of solvers for different programming environments? I know that Julia has a relatively handy jump interface for model formulation, and many open source solvers providing API to call from jump.
Yeah, so I've actually interacted with the Julia team that is also doing the an integration with Highs quite a bit. We focus this presentation specifically on the Python ecosystem and the tools available in Python. So no, we have not. If you really want performance, like I said, like at my day job when we prototype algorithms, I always do it in Python, or you can do it in Julia. These higher level things to just make sure you have something to work, and then you go into a different programming environment. Maybe for production, you need to implement it in a lower level C++ or Fortran. So that's definitely going to be quicker and more efficient, but there's different concerns there. I guess that's a long way of saying no. We just consider Python in this presentation, but there are a lot of packages available in other places like Julia. MATLAB has GLPK. I think I know that Octave has a GLPK built in. That's their linear programming and integer programming solver. So there's lots of ways and lots of different programming languages that have interfaces to these low-level solvers.
Okay, great. Thank you. I encourage all of our audience members to try to contact these speakers in the Gather Town a little bit later if you're going to be there, or you can send private messages in AirMeet itself. So if you do have any follow-up questions, or maybe you think of something later that you want to ask the speakers, please message them. Thank you again for a great talk. And thanks for joining also for the moral support, Dayton. I'm glad you were here. So we have a 5-minute break before the next talk in the general session. So I'll let you all go. But please join us for the next talk, which is going to be building SciPy kernels with Python. So I'll see you all in a couple minutes.